Hi, good morning. Today we will see LMTD analysis of parallel fluid exchanger. So, why it is called as parallel fluid exchanger means both hot fluid and cold fluid will be travels in the same direction. So here TH is there, THI is called as hot fluid or hot fluid inlet temperature. Here TH naught will be there, that is hot fluid outlet temperature. Similarly, TCI is there. TCI is called as cold water or cold fluid inlet temperature, and TC naught it is called as cold fluid outlet temperature. So here delta T1 is the temperature difference between the fluids at section 1, that is THI minus TCI, that is at inlet condition. Similarly, delta T2 is temperature difference at outlet conditions, that is TH naught minus TC naught will be there. So this is the temperature difference at section 1 and section 2. This is section 1 and this is section 2. The temperature difference is called as here it is called as delta T1 and here it is called as delta T2. So in order to apply the LMTD analysis, we need at least three temperatures, that is any three temperatures or four temperatures, that is THI, TH naught, TH naught, TC naught and TCA. So then only we can apply LMTD analysis. Otherwise, we need to go for NTU method. Let us go to the LMTD analysis. Before going to the LMTD analysis, for more videos on heat transfer, you can subscribe my channel. Thank you. Next one is let us go to the LMTD analysis. So these are the assumptions we are taking in LMTD analysis. The assumptions will be first one is U. U is overall heat transfer coefficient is considered to be constant throughout the whole length of the heat exchanger. So throughout the length of the heat exchanger, U is assumed to be constant. Next, the properties of the fluid remains constant. So after steady state only, we are going to take the properties in consideration. Therefore, we are assuming all the properties are remains constant. Next one is we are assuming no loss of heat to the surroundings. So here we are assuming heat will be given by the hot fluid and heat will be taken by the cold fluid. That's all. There is no other heat losses. That means MH, CH, THI minus TH naught is equal to MC, CC, TC naught minus TCA. So by using this equation, we can, if you know any three temperatures, we can find other temperature also. So if you know all the four temperatures, then only we can apply LMTD analysis. Next thing is change in kinetic energy and potential energy are neglected. So there is no change in kinetic energy and potential energy we are assuming. Next one is temperature of the fluid remains constant across the heat exchanger. So the temperature, once it is reached steady state, that value will be remains constant with respect to time. So that is called as temperature of the fluid remains constant with respect to time across the heat exchanger. Next one is temperature difference between the two fluids is not constant throughout the heat length, because now if parallel fluid exchanger, the temperature profile will be hot fluid will be high temperature and the outlet will be low temperature. Cold fluid inlet will be low temperature after gaining heat. Now it will be high temperature. This is THI and this is TH naught. This is TCI and this is TC naught. So TC naught. So this is called as delta T1 and this is called as delta T2. So this temperature difference between the hot fluid and cold fluid will be maximum at the inlet condition and it is minimum at the outlet condition. So the temperature will be goes on decreasing throughout the temperature difference will goes on decreasing throughout the length of the heat exchanger. So our aim is to find an appropriate mean temperature difference so that it will be constant throughout the heat exchanger. Since it is in terms of logarithmic, that's why it is called as log mean temperature difference. LMTD means log mean temperature difference. So let us go to the parallel flow heat exchanger and analyze how we are deriving the LMTD for parallel flow heat exchanger. Okay, this is a parallel flow heat exchanger. This is a parallel flow heat exchanger. So here this will be uh, cold fluid, I mean hot fluid inlet temperature, and this will be uh, hot fluid outlet temperature, and this is TCI, cold fluid inlet temperature. This will be TC naught, cold fluid outlet temperature, and this is delta T1, that is the temperature difference between the hot fluid and cold fluid at section 1. This is called as delta T2, that is temperature difference at the section T2. So that this delta T1 is nothing but the temperature difference of THI minus TCI here. This delta T1. Here delta T2 means this temperature difference, that is TH naught minus TC naught. THI minus TCI is delta T1. Now let us take heat given by the hot fluid. So in heat exchanger, it is a device where heat will be transferred between the two fluids which are maintained at different temperatures. The fluid which is maintained at high temperature is called as hot fluid. The fluid which is maintained at low temperature is cold fluid. Everybody know the definition of heat exchanger. So here Q is equal to MHCH THI minus TC, THI minus TC, THI minus TH naught, not THI minus TCI, THI minus TH naught. So it is called as TH naught is called as amount of heat given by the hot fluid. So here MHCH is called as MHCH is called as heat capacity, capital CH, and amount of heat taken by the cold fluid will be Q is equal to MCCC TC naught minus TCI. So here MCCC is called as heat capacity of the cold fluid. So from this we can write 1 by CH is equal to, if you write from this we can write 1 by CH is equal to 1 by CH is equal to what you can write THI minus TH naught by CH. Similarly, 1 by Cc can be written as this is Q divided by Q, divided by Q. Here 1 by Cc can be written as Tc naught minus Tci by Q. Next thing is let us consider small area. Let us consider small area dA. dA is the small area. So in this now temperature difference will be delta T. So for that heat transfer rate will be dq, and the dq can be written as dq is equal to, for the small element of the length of the heat exchanger at a distance of x will be dx, no, length will be dx. So for that heat transfer rate is can be written as dq is equal to, u is overall heat transfer coefficient, th is hot fluid temperature, tc is a cold fluid temperature. That small element, the surface area of the heat exchanger will be dSA. So this is the equation. Next thing is from this equation we can write one second. From this equation we can write Q can also be written as heat given by the hot fluid is minus MHCH DTH, that is the hot fluid temperature at this point, hot fluid temperature, change in hot fluid temperature throughout the length. And similarly heat taken by the cold fluid for that length will be dq is equal to, this dq is equal to, here we can write now dq is equal to heat taken by the cold fluid, that is mccc dtc, that is equal to this mhch is called as heat capacity ch, and mccc is called as cc, that is heat capacity of the cold fluid. So from this expression we can write dth is equal to dq by this is called as ch, and from this expression we can write dtc is equal to dq by this is cc. That means we can write dt is equal to minus dq by ch and dth. Next one is dtc can be, we can write dq by this is heat capacity of the cold fluid cc. Now, now we will go to the actual derivation. Let us take this thing. Let us take temperature difference. That is this one. Temperature difference at distance of x for the element of dA. No, we can write dTh minus dTc. That is the temperature difference between the two fluids. So that can be rearranged as d is equal to Th minus Tc, that is equal to, just now we have derived now dTh is equal to minus dq by ch and dTc is equal to my that is dq by cc. So just now we have derived these equations. Based on these equations, we can write here dTh is equal to this value dq by mhch and dTc is equal to, we can write plus 1 by mccc. Okay, so now that is dth minus dt, no, th minus tc is called as th minus tc is called as delta t at distance for the element dA. So we can write d of dt is equal to minus dq. This can be written as 1 by ch plus 1 by cc. So that is once again d delta t, that is equal to dq formula is there. Dq is equal to uda delta t, that is there. That is the general formula which is given for the heat transfer and heat exchanger. dq is equal to uda delta t. That there we are in terms of overall heat transfer coefficient. There we are substituting here in place of dq. In place of dq we are substituting 1 by ch plus 1 by cc. Now we are integrating the this equation in the limits of inlet section to outlet section, and here this delta t is there. Now we are taking to this side, we will get 1 by delta t. So the equation will become integral delta t1 to delta t2 d delta t by delta t. So here we will get minus u 1 by ch plus 1 by cc. All these terms will be constant, and integral of dA in the limits of 1 to 2. Therefore, this one now integral of delta t will be so integral of 1 by x will be log x now ln of delta t in the limits of 1 and 2, inlet section and outlet section, that is delta t1 to delta t2. So that means you get that is equal to ln of delta t1 ln of delta t2 minus ln of delta t1. So log a minus log b, no, will get ln of delta t2 by delta t1. So same thing will be here represented. We will get integral of 1 by delta t will becomes ln of delta t2 by delta 1. So this integral of dA will be a only, because if you integrate the small area, you will get the total surface area. The total surface area will be a only, minus ua by 1 by ch plus 1 by cc. So here now in the first equation, 1 by ch will be derived as 1 by ch is equal to thi minus th naught by q. Same thing we are putting here, thi minus th naught by q, and 1 by cc now we have derived it as tc naught minus tci by q. Same thing we are keeping here. This is tc naught minus tci by q. This value we are putting here. This value we are putting here. So q common, you will get minus ua by q, thi minus tci. Here if you make minus, rearranging the terms, thi, and we are bringing this tci, no, we are bringing this tci here, we will get minus tci, and we are making minus common, rearranging the terms so that here minus th naught is there. If you take minus common, th naught, and plus is there, here you will get minus minus common, you will get minus tc naught. So this is th naught and tca this. So this temperature will be, difference will becomes the delta t1. This temperature will becomes the delta t2. delta T2. So minus sign is there, send minus side inside, will get delta T1 minus delta T1 minus delta T2. You send minus side inside, you will get delta T2 minus delta T1. Therefore, you will get the equation as heat transfer in a heat exchanger will be in terms of uh, QUA, and the average temperature is delta T2 minus delta T1 by ln of delta T2 by delta T1. Since this average temperature in terms of log, it is called as a log mean temperature difference. Log mean temperature difference, or simply LMTD. LMTD. So this equation is there. We are comparing with the general basic equation Q is equal to UA delta T LM. So by comparing these two equations now, equating these equations, we will get the expression for log mean temperature difference will be delta T2 minus delta T1 by ln of delta T2 minus by delta T1. Or if you take minus sign and we can rearranging the terms, we can also be written as delta Tm is equal to delta T1 minus delta T2 by ln of delta T1 by delta T2. So this is the expression for log mean temperature difference for a parallel fluid exchanger. I hope you understand this difference derivation. Thank you for watching. For more videos, you can subscribe my channel. Thank you.